Pleasure to thank the organizers for inviting me here. I'm always glad to stay in Korea and to enjoy this lovely place. So I will talk about this joint project with Daniele Fenzi and Jean Vallès. It's quite a long project, I have to admit, but this time probably we are finishing it and it will appear reasonably soon on the archive. So, what is a triple plane? In general, definition, a triple cover for me is a finite morphism f from x to y, where x and y are smooth surfaces. Of course, we can make this definition much more general, but for our purposes, this is okay in this talk. And we also make the following assumption. Of generality. This assumption is the following: the branch curve B in Y has a finite number of cusps over which f is totally ramified, and in the other point of the branch locus the ramification is simple. Over the degree C, yeah, sorry. Thank you. And the rest of B, the ramification is simple. So we have a situation like that. This is X, this is F, this is 3 to 1 morphism, this is Y. Here we have a branch curve with at most a finite number of cusps. In this case, the ramification locus that I denote by R is smooth, and this is precisely the normalization of B. R is in X. Note that this assumption on simple ramification outside this finite number of points means that this cover is, is not a Galois cover. Otherwise, the Galois cover would be totally ramified everywhere. In particular, the assumption on ramification. Yeah.
There is a double point or a single point.
Yeah, exactly. There is the push forward of B is this curve R plus another curve over which there is no ramification. And these two curves touch them in the preimages of the cusps. Exactly. This is the formula. F is not Galois. Okay, so
you assume that you have ordinary double ramification. ramification over the branch curve. Because otherwise you could take cube roots of f.
Sorry?
Right, the assumption is that generically...
Generically there is double ramification, yeah, simple, and the rest, the ramification is simple. Simple, I mean, yes, one point with ramification 2 and one point in which there is no ramification. Okay, so you cannot avoid cusps in general. I mean, there are cases in which there are no cusps, but in general, this is the general situation for a triple cover between smooth surfaces is this one. So, the aim is to classify triple cover with these invariants, with Pg equal Q equal 0.
Why is P2?
Why? Okay, when y is P2. I was just saying this. In this case, I will call about triple plane. Okay, now the first result that we have is this table that I drew there. This table provides all the possible invariants. Okay, let me see that such a triple plane okay, from now on this condition or ramification is assumed, so I will say just triple plane. A triple plane f from x to 2 has a branch curve B with of degree. One can show that the degree is even and the number of cusps is divisible by 3. Call H the push forward of a line, okay, where L is a line. The pullback, the line, exactly, and the genus of this curve is called the sectional genus of the triple plane. So, first result, the numerical possibilities, so let f x p2 triple plane the numerical possibilities for B, I wrote the BH kx squared G of H are shown in the table. So, we can, I will not prove this, but this follows from the theory of Miranda on triple cover, something else. But just let me say that one can do computation and show the only possibilities for a triple plane with pitch equal Q equals 0. I forgot always this assumption because... So, when you have a triple plane with G equal Q equals 0, the only possibilities for B, H, Kx squared, G of H are shown here. So there are 12, in principle there are 12 numerical possibilities. The Problem is show that which of them occur and which not, if they all occur.
But where does this table come from? Are there some basic relations between these invariants?
Sorry?
Where does this come from?
Yeah, there are some relation. Yeah, there are some relation, of course. Because I will tell you something. When you push down the structural sheaf of OX, you have a splitting of OP2 plus a vector bundle of rank 2. You can compute the Chern class of this vector bundle, and they are related to this invariance. And so you can make some computation, and you see that using also classification of surface, Migaoka-Yau, and something else, you can bound the invariance, see what happens.
And another basic question. Maybe
Yeah, of course.
You will address it later, maybe you were going to, but what is the codiary dimension, for example?
Yeah, this is an interesting question. So, let me say, these cases partially were treated by Duval in the 30s. Not completely, but he gave a partial classification of this using synthetic projective geometry. Nowadays, it's quite difficult to read this paper, but I read them. I'm quite convinced that they are more or less okay, but the language is very different from ours. We reworked all the classification using completely different ways, and we arrived at more or less at the same result. He forgot something anyway. These are rational. These are all rational. In this case, these are completely new. We have these cases here. These are completely new. Here we have rational surfaces and one Enrique surface, which is a Rye congruence. These cases, we don't know if they exist. This is the open problem. If you can prove that these cases exist. If, for instance, this case, the last one, would be a surface of general type, we can prove this. But we don't know if they exist. The problem is that you must, in order to show the existence of these planes, you must construct these triple planes, you must construct some vector bundle of rank 2 on P2, and the more you go down in this table, the more spatial this vector bundle becomes. And so at a certain point we are not able, already in this case, which are new, completely new, they are not present in classical literature, it was really, really hard to find the vector bundle. And this, there is a lot of, I will say this, there is a lot of interaction with the theory of Steiner bundles. So, I mean, in these cases, we were not able so far to identify the bundle. Yes?
There seems to be an easy inequality here, that G of H is less than 12.
Yeah. G of H cannot be.
Is that very easy to explain? Why?
You must do. If I do this, I can show you the paper later. If I do this, I have no time to explain other things. But I can show you after. It's just a numerical computation. This is not difficult. So. Okay, so let me say. Okay, so let me write the other.
Possibility of the fundamental group in this case?
We don't know. We don't know if they exist. The problem is that this, how can you compute the fundamental group of such a thing? The only way will be to use the fundamental group of the complement of the branch curve. But this branch curve will be, for instance, you see, something of degree, so 26 with 3 times 67 cusps, and they will be not in general position, sure. So in this way, I think it's hopeless, but maybe there is some more clever way that we don't see. But we don't know if they exist. We don't know if this exists. This is numerical possibilities. On the other hand, we are not able to construct the surface from below, starting from the curve, and we are not able to construct it from above, starting from the vector bundle. So this case is really challenging, but so far we don't know. This is so. Theorem 2. We can give a complete classification of cases 1, 2, 6, and the partial classification of 7. Partial means that it's almost classified, there are only few cases open. that leaves only very few cases open. I will explain this. Okay, before entering in details, let me make some comments. Remark 1. Cases 1-6, as I said before, were considered and partially classified by Duval, 1930, 1935, using synthetic projective geometry. Classical, let me say, projective geometry. It's actually quite amazing that he arrived to this classification, even it's partial, because I mean the methods used are really elementary. But anyway, he arrived to say something about this. The case 7 that we have is completely new. The examples in 7 are completely new. And they also provide counterexamples to a claim made by Bronowski. In 42, Bronowski, in a paper on the Bulletin of the Non-Mathematical Society, claimed an inequality about triple planes with this invariant, and this inequality turns out to be false. I will explain. So, they also provide counterexamples to a wrong claim made by Bronowski in 1942. He claimed that one should have h lesser than or equal to b squared. And if you look at the table, this is true until case 6, but in case 7 this fails. Fails from cases. So, and this exists. And in fact, you look here, case 7 is 3h is 66 and b squared is 64. And there is no equality. The equality is on the contrary. So, it was very hard to understand Bronowski proof. In contrast with Duval, Bronowski is really difficult to understand. Duval, you at least understand what he's doing. Bronowski is very difficult to understand what he's doing, but nevertheless, we read this paper trying to understand his mistake, and at the end, we realize that at a certain point, he makes an assumption that there is a curve algebraically equivalent to this R0 here and distinct from it. But this cannot happen when this one has negative self-intersection, because in that case, this curve will be rigid. And starting from case 7, this curve has negative self-intersection. So he did not realize that this curve could be rigid, and then when he makes this assumption on moving it algebraically, he arrived to this conclusion. And in fact, this is true in the case where this curve can be algebraically moved in the surface. But when this curve is rigid, no way. In fact, there are counterexamples. But it was painful to understand what he was doing. Anyway, so let's say 2 words about the methods. Yes?
So you can construct a surface like in 7
Yes.
to prove the existence of a curve like that. Is that right?
The curve exists a posteriori because, no, we start from the vector bundle. So I will explain to you as a vector bundle technique. You can construct the triple plane starting from the Chernyshev module. Is the sum and in the decomposition of Lavoisier of X. When you construct this and you show that there is a section in a certain symmetric product that I will explain, then the surface exists. A posteriori, this proves that the curve exists. I have no way to construct the curve before. I know no way to construct the curve. I know that the curve exists because the triple cover exists. But I cannot do the other way around. I cannot start from the curve. These casts must be in very special position, you know, Zariski problem, I mean, and so on. You cannot hope that the cusps are in general position. So I think that the construction of the curve is complicated, but I would like to see a construction of the curve, but I don't know if this is feasible. Probably you can do it by computer algebra in the sense that our method allows us to encode the construction of the vector bundle in Macaulay too, so you can construct locally the cover and then you can compute the branch locus with Macaulay too and have in principle have equation for the branch curve. But it's a posteriori method. Okay. So our method is a combination of adjunction theory following the modern treatment by Beltrametti e Sommese and vector bundle technique in particular, analysis of Steiner bundles of the form the resolution is this one. And this is M, this is a metric of linear forms. It's a B minus 2 so a Steiner bundle, this B will be that B. This B will be the Steiner bundle corresponding at that case in the non-split case, I will explain. So a Steiner bundle is a bundle which has this kind of resolution, so it just means that you see here minus 1 is O, so there is a matrix B minus 2 times B minus 4 matrix of linear form giving this Steiner bundle of rank 2 on P2. Okay. Well, okay. So, what is the bundle? The bundle is a Chernyshev module of the cover. We are over C. I didn't say this, but we are over C. We work over C. So the trace map gives a splitting. You push down the structural sheaf of X and you obtain OP2 plus epsilon E, and this E is a rank 2 vector bundle on P2 called the Chernyshev module. Oh, Chernyshev bundle. Chernyshev bundle. The name comes from the fact that if you take a cubic equation, you can use a trigonometric transformation in order to get rid of the term in x squared. And in some sense, you are taking trace-free equations. And so locally, when you split this locally, this part corresponds exactly to this square-free, this equation without term in x squared. So this is the reason why it is called the Schirnhausen bundle. Miranda called it this in his paper about triple covers. Okay, so Miranda showed that the treble cover is reconstructible using the sheaf and a section, a global section, sigma, different from 0, in, let's say P2, but this is more general anyway. So Miranda's theory say, okay, you want to reconstruct the triple cover, you need the bundle, but you also need this section here. This section gives an element, if you want, this is a trisection in the projective bundle associated to it. So you can see your smooth triple cover as a trisection of a projective bundle. Let me write it here. So, in fact, such a section realizes X as a trisecting of the projective bundle P of E dual, more precisely, we'll have X in this linear system of P E dual of 3 times, and you have this, so you have P upper star of lambda 2 of E, where pi is the bundle map. So you must do 3 things. You must construct the bundle. You must see that this vector space is not empty, otherwise no hope. And when this vector space is not empty, you must be able to find a section such that the corresponding trisection here is smooth. So usually finding the bundle in case 7, which is the most difficult case, finding the bundle was not difficult, I will explain, and the section can be found. The difficult thing is to show that this is smooth, and this can be done by computer algebra.
So is that X is smooth, is that equivalent to the genericity condition on the curve?
Yeah, if you want, yeah. Yeah, it could be totally ramified. For instance, in the Galois case over a smooth base is also smooth. So, but anyway, yes, of course, generically is the same thing, yeah. But you can have some Galois case or some totally ramified case in which X is smooth and it's not generic.
Is it an easy translation, just the genericity condition, some easy condition on that sigma?
The vanishing of the section must be of a certain order, I think, and I should think about this.
You can just work in terms of sigma.
Yeah.
Not even look at that.
Yeah, but it's not easy to address directly sigma. For our computation, it was easier to write down equations for this inside this bundle. Sigma is abstractly can be difficult to handle, but when you can give equation for this, if you're lucky. And so yeah, but I think that yeah we can work down local condition for sigma equivalent to the genericity of the ramification. I think so.
Yeah, if this bound is generated by global sections, the generic section produce your triple cover.
Yeah, generic if you can have some generic section giving a smooth bundle, I mean.
It is globally generated.
If it is globally generated, yes. This is a result by Casenati and Dekedal and other people. Yeah. If this is globally generated, this is a good observation. If this is globally generated, the general section provides a smooth X. And I mean a general triple cover. But if this is not globally generated, you are in trouble and you must show directly the existence of a good section.
But I mean, Francesco, if the branch curve
Yeah.
is smooth and has ordinary cusps,
Yeah.
this implies the smoothness.
Yes, of course. Yeah. But it's not equivalent. I mean, it could be a Galois cover branched over, a Galois cover totally branched on the branch, and it could be smooth as well.
Each connected component is either a smooth curve, which is double, or it is
Yeah, exactly.
cuspidal.
Yeah. For X smooth is this. Yeah. So if this is globally generated, okay, the general section gives the triple cover. If this is not globally generated, it can also happen that you have the smooth cover, but you must show this by hand, and this is painful. But in some cases, it's possible to do. Okay, so let me explain what means split and no split. Yeah, no. Theorem 3. Let me call theorem 2a. The split case so in cases 1, 2, 3, the bundle E splits as a sum of two line bundles. More precisely, in case 1, we have E O minus 1 plus O minus 1 over Q2, of course. So in this case, X is S12, the cubic scroll in P4. You have this cubic scroll in P4. And the vector bundle map is just the projection from a general line. B is the tricuspidal quartic curve. There is up to projectivity, there is just one tricuspidal quartic curve, and this is the branch in this case. Okay, case 2. E is O minus 1 plus O minus 2, and X, you can see X in P3 as a cubic surface. Okay, F is the projection from a general point, external. And B is a sextic with, okay, 6 cusps on a conic. This was already known by Zariski that if you have a sextic with 6 cusps, this sextic is branch locus of a triple cover, of a triple plane, if and only if the 6 cusps lie on a conic. This is because the fundamental group of the complement in that case is the free product of Z2 and Z3. Whereas if the cusps do not lie on a conic, the fundamental group is the direct product. Okay, case 3. The bundle is O minus 2 plus O minus 2. And in this case, we have X is the blow up at 9 points of Fn. So we have a map sigma from X to Fn, blow up on 9 points. N is just 0, 1, 2, or 3, and H, which is so the net giving the triple cover in this case, is 2 times C0 plus N plus 3 F minus sum of this equation. Yeah, of course, this will be the full sigma per star of this, but let me just write in this way. And this is the section of negative self-intersection. This is the fiber of this Fn. Yeah, this is Fn. Well, this, for instance, when n equals 0, here you have the this is the quadric, and you have the blow up of the quadric at 9 points, and you are just using the curve of B degree 2, 3 through these 9 points. The curve of B degree 2, 3 intersects in 12 points, minus 9, you have 3. This is the cover. Okay, this is the easy case. Let's go to the non-easy case. Theorem 2b. The non-split case. Okay, in cases 4, 5, 12, E is not split. More precisely, it has a resolution zero, OP2, 1 minus B, B minus 4, OP2, 2 minus B, B minus 2, E, 0, so it is a Steiner bundle. So, this you prove this by looking at the cohomology of E. Using the fact that you have this invariance, you can compute some cohomology group of E and some twisted power, so some of its twists, and so you can use Beilinson theorem. And using Beilinson theorem, you arrive at this kind of resolution. Quite surprising that it's so simple. And so you see, it's a Steiner bundle. So you have a matrix of linear forms here. So it's the most simple possible resolution for something which is... yeah.
How did you get this table? I thought the table was a consequence of the theorem.
No, the table is numerical computation using Miranda's formula and the fact that...
Numerical
numerical computation using Miranda formula and the fact that k square must be, since you have pg equals 0, k square is almost 9, and so you make some computation, you arrive at a quadratic equation using this formula of correspondence by Severi and so on. This quadratic equation must have natural solution because these are just natural numbers. You made a case-by-case check, and you see that these are the only possibilities.
Francesco explained all of this in detail before you arrived.
But case is a U with question mark. 8 up to 12 are still to be constructed.
Yes, we don't know if they exist. We also would like to see their existence or a proof of their non-existence, but this is the big mystery in the story.
Francesco, one little point when you're writing this E, is it one bundle or does it depend on parameters?
Steiner bundle depends on parameter because here you have this matrix, but in some cases, in cases 7 for instance, you cannot take the general one. You cannot take the general one. It depends on unstable lines. You must have unstable lines. If you don't have stable lines, you don't have surface. This is, yeah, I will explain. Yeah, in the other case, you can take the general one. But starting from 7, the general one has not this famous sigma section. There is no section, so not in the triple symmetric product. So you need to look for spatial bundles. And in case 7, we were able to identify what spatial means, whereas in the other case, we are still unable to identify what spatial bundles means. The general ones...
Basically, the usual problem, the E,
yeah.
if you can construct at all, has to be very superabundant.
Yeah. Yeah. In this case, in case 7, it must have unstable lines. I will explain. So it must be spatial from the point of view of Grauer-Mulich decomposition. Okay, so more precisely. In case 4, X is the blow-up of P2 at 13 points, imposing only 12 conditions on quartics. Moreover, H, in this case, so the net giving the triple cover, is given by 4L minus sum of... Again, this must be intended as the pullback of a line in the blow-up, but I guess I wrote it this way. Okay, so, I mean, quartic curves depends on... yeah, exactly. They depend on 14 projective parameters, and in principle, 13 points impose 13 conditions, but in this case, these points are not in general position, but are in special position. They impose just 12 conditions. It is possible to construct these points by using some kind of Cayley-Bacharach construction. And so 14 minus 12 is 2. This is a net, and this gives a triple cover. The self-intersection of 4L is 16, minus 13 is 3. So you have just a triple cover. This is case 4. Case 5. In case 5, so X is the blow-up
Projections of rational surface.
Yeah, this is another way to see them as a projection, for instance, of surface in Grassmannian. You have this kind of congruencies of type 3n in the Grassmannian. They were classified by Gross. And if you since there are these congruencies of type 3n, then you can project from this n second planes obtaining the triple covers. And this is one of these cases. No, it does not. But they are all rational. The example we have are all rational until case 6. In case 7, we have rational surfaces and one Enrique surface, the Ray congruence. The other case we don't know, but for instance, if this would exist, this would be of general type. You're right. Okay, so X is the blow up of P2 at 15 points, and H is 6 times L minus the sum 2EI minus sum from J from 7 to 15 EJ. So you see, in this case, we are the net is given by sextic plane curves having 6 nodes and passing through 9 fixed other fixed points that are not in general position anyway, but we can do it. Equivalently, you can see this as the blow up. You see, this is just a double hyperplane section of a cubic surface in P3. So you are blowing up this cubic surface along 9 points, but these points are not in general position. In fact, you can show that these points lie in the intersection of this cubic surface with a twisted cubic curve. 3 by 3, 9. There is some geometry involved here, but I have no time to explain everything in details. Any case has a lot of geometry inside, but okay. Let's just explain the cases, and then maybe if we have time, I will go in details in some of them. Case 6. Here things start to be subtle. In case 6, we have this situation. The situation is as follows. There is a determinantal cubic threefold Y inside P4. By Tom Porteus, these are 6 nodes, expectedly, but the general one has 6 nodes. We can show that there exists a smooth Bordiga surface inside Y containing all the nodes. There exists a smooth Bordiga surface containing all the nodes. As a for the Bordiga surface, they are a smooth point, but they are nodes of the threefold. So, X is just the blow up of this Bordiga surface at the 6 nodes. So, of course, you must show the existence of this surface, and you must play with tritensors, because this Bordiga shift, this Steiner bundle, you can see in terms of tritensor, and then you can reverse the tritensor, obtaining something on P4, and then you see that this gives you a threefold, this determinantal cubic threefold. So just it's complicated to explain now in few minutes. So anyway, it's playing with the Steiner bundle and transposing the tritensor, giving it, you obtain a resolution of something in P4, and this is supported on this determinantal cubic threefold, and you can also recover the Bordiga from this. Yeah?
Can you remind me what is a Bordiga?
Yes, I will, because...
B is 7.
Huh?
Here B is 7.
Here, in case 6, B is 7, I think, yes. B is 7. Yeah, yeah. Yeah, I will always remind, because this gives me the H. So the Bordiga surface...
So it's the one which gives the cubic surface.
Yes, of course. When you have a Steiner here, exactly, because you see, you have B7, so you have 3, 5, and so on. And so when you transpose the tensor, you have the resolution of a determinantal cubic threefold of a sheaf supported on a determinantal cubic threefold in P4. Well, Bordiga surface Bordiga surface. Okay, is blow up of P2 at 10 points embedded by for L minus sum of EI in P4. So this is the Bordiga surface. You take sextic through 10 points. Okay, so 16 minus 10 is 6. So this is a surface of degree 6 in P4. Okay, and when you blow up 6 node, the 6 point here, you obtain H. You make a computation, I mean. It is 7L minus sum . This is 7 and this is 2 here, because actually this embedding of the Bordiga surface inside Y is given by the first adjunction map with respect to H. So if you want H, you must add K, subtract K, and you obtain this. You can show that this embedding is given by the first adjunction map with respect to H. Anyway, this is the final answer. And so case 7, sorry, I cannot give a lot of details, but if you want, I mean, the first adjunction map is just this contracts this 6 divisor, 6 minus 1 curve are contracted, and you obtain this. And then when you want to come back, you must add, you must revert adjunction, so you must subtract the canonical and this one. Okay, anyway, this is. Case 7. In this case, so far, the Steiner bundle was general. In this case, this is not true anymore. In this case, E is not a general Steiner bundle with this resolution. So in this case we have is 8, so 4, 6. Yeah, of course you have some kind minus 7 there. 8, so minus 7. Minus 6. If it is correct. 2 minus b, yeah? In fact, you need that the bundle has the so-called unstable lines. And lines L in P2 such that E, well, it's not really E. Let's consider the other shape. Twist this by 7, by 6. You have this one. Okay, take this. So F is E of 6. Right, yeah, minus 1, yeah. When you restrict F to L, you have, okay, so this has first general class 4, and you want a splitting of this type. Minus 4 maybe. I wrote something 4, yeah. Yeah, because it's 4. So you see, the point is that the generic split, here you have, the generic splitting will be 2-2, will be this balanced one by Grauer-Mühlich. You will have lines with splitting 1-3, but you want more. You want line with double split, with splitting doubly degenerate. So O4. If you have such a lines, then you have the surface. This is the result. Otherwise, nothing. It is known that for such a bundle, the number, let me call it alpha 1 as in the paper, of unstable lines is either or proposition X exists if and only if the number of unstable lines is between 1 and 7. Yeah, but we started 5 minutes, right? No. I have 5 minutes? Less than that. Okay, so thank you. Okay, so anyway, this is a Schwarzenberger bundle, it's called. This is logarithmic bundle. So when we have stable lines between 1 and 7, so this is not the general one, because the general one will have no unstable lines. General Steiner. So in this case, X exists, and for instance, H1 equal 7, this is Reye congruence. Of type 3,7 in G1 P3. This is Enriquez. And when alpha 1 equals 6, this is projection of Alexander surface, rational surface, from the unique I'm finishing. 6-second line. There is this very special Alexander surface in P4, and this has a unique 6-second line by Lebard's formulas. You project from this, it has degree 9. You project from this 6-second line, you obtain a birational model of a triple cover. And finally, the other cases are other cases, alpha 1 equal 1, 5 other rational surfaces that we can describe. And their existence has been proven by, the existence has been proven by hand, and the smoothness has been proven by using Macaulay 2 computer algebra. And so this is, since my time is over, I think this is the end of the story. Thank you very much for your attention.